Welcome back to the deep dive. If you've been keeping an eye on AI lately, you've seen the huge investments, the incredible capabilities. But maybe you've also noticed something else bubbling under the surface: the energy cost. It's becoming a serious problem.
Oh, it's way more than just a footnote. The sources we looked at paint a pretty stark picture. Get this. U.S. firms are spending more every year on AI data centers than the inflation-adjusted cost of the entire Apollo program.
Wow. Every single year.
Every year. And the projections based on that, they're frankly staggering.
Yeah.
By 2030, these centers could be eating up something like 10% of all the energy produced in the U.S.
10%?
Yeah.
That's not sustainable. Continued scaling just seems impossible on that trajectory with current tech.
Exactly. Which brings us to our mission for today. We're diving into some fascinating research that proposes, well, a pretty radical new path forward. It's a probabilistic hardware architecture called the Denoising Thermodynamic Computer Architecture, or DTCA.
DTCA, okay.
And it's powered by a new algorithm, DTMs, that they claim fixes some fundamental flaws in how today's AI models work, slashing the energy use.
Okay, the claim itself sounds almost unbelievable. Performance like today's GPUs, say for image generation, but is it really 10,000 times less energy?
That's the number they put forward. 4 orders of magnitude less.
That feels like science fiction territory. How is that even physically possible? And, if it is, why aren't we already doing it?
Well, that's the big question, isn't it? To get there, we first need to understand just how inefficient our current main systems, like large language models, actually are. They're built really specifically for GPUs.
Right, and that's the whole hardware lottery thing, isn't it? GPUs weren't designed for AI at all.
Not even close. They were for graphics, video games. It was almost an accident, decades later, that their parallel processing turned out to be good for the kind of math AI needs.
So we basically lucked into a solution.
We did.
Yeah.
But because the big models, the LLMs, were then designed to fit those GPUs, we're now kind of locked into this specific hardware-software marriage. And it's, let's just say, not optimized for energy efficiency.
So we've poured billions into optimizing for hardware that was fundamentally the wrong tool for the job, energy-wise.
That's a fair way to put it. And it explains why you see all these other efforts now, right?
Well,
people exploring photonic computing, compute in memory.
Trying to find a way out. But the sources we have suggest those are maybe just scratching the surface, fixing components, not the core system.
Exactly. They're trying to make the individual calculations cheaper. But this research argues that for a huge leap, like 10,000x, you need to fix the system itself. You need a different algorithm that works better with the underlying physics.
Okay, so if the GPU pairing is inefficient, what's the algorithmic problem this research claims to solve? You mentioned energy-based models, EBMs. Let's unpack those.
Right, EBMs, they're a type of probabilistic model. Think of it like this. They learn the shape of the data. Imagine all possible images. An EBM learns to assign a low energy value to common things like pictures of cats or dogs, and a high energy value to things it hasn't seen much, or just random noise. It sculpts this energy landscape.
So the familiar data is down in deep valleys, and the weird stuff is up on high mountains. Makes sense.
Precisely. But here's the catch with a traditional approach, using one big monolithic EBM. It runs into what these sources call the mixing expressivity trade-off, the meet-meet.
Okay, sounds technical. Can you make that more concrete for us?
Sure. So real-world data is complex. It's multimodal. Think about telling apart images of airplanes versus dogs. These are distinct modes in the data. To model that distinction really well, the EBM's energy landscape needs to be complex and rugged. You need a deep valley for dogs, a deep valley for airplanes, and crucially, a very tall energy barrier between them. Let's call it delta E.
Okay, so the height of that barrier, delta E, represents how well the model separates dogs from airplanes. It's expressivity.
Exactly. Higher barrier, better separation, more expressive power. But here's the problem. How do EBMs generate new samples? They use iterative methods like Gibbs sampling. These samplers work locally. They take small steps around the energy landscape. They don't have a bird's eye view.
So they're exploring the dog valley.
Right. And the probability of that local sampler just randomly making a huge leap, hopping over that massive energy barrier, delta E, to get to the airplane valley, it's exponentially small, like vanishingly tiny.
So the sampler gets stuck. It's like it's trapped in the dog valley and can't find the airplanes because the mountain pass is just too high to cross randomly.
You got it. That huge barrier needed for expressivity literally grinds the sampler to a halt. So as you make the model more powerful, increasing delta E, the time it takes to get a good representative sample, the mixing time just explodes. exponentially.
Okay, now I see the energy cost. You're burning massive amounts of computation just waiting for the sampler to sort of get lucky and jump the barrier.
That's the essence of the MET. Performance is tied directly to how hard it is to sample. And that's why those big monolithic EBMs they call them, never really took off commercially. They were just too slow, too energy hungry.
The sources even showed that on the same hardware, an MEBM could use orders of magnitude more energy than this new approach, purely because of that slow mixing.
Correct. Which brings us to the proposed solution. Denoising thermodynamic models, or DTMs.
DTM. So how do they solve this getting stuck in the valley problem? Do they just find a shortcut over the mountain?
They cleverly avoid the mountain altogether. DTMs blend EBM ideas with another concept, diffusion models. But crucially, they don't try to build that one single, incredibly rugged landscape for the whole data set.
No single Mount Everest between dogs and airplanes.
Exactly. Instead, they use a whole sequence of much simpler EBMs, many of them chained together.
Okay.
Each little EBM in the chain performs just one small step in a gradual process, like slowly removing noise from an image to make it clearer.
Ah, so instead of one giant leap, it's like a series of small hops.
Precisely. Think of it like breaking down that giant high jump bar into, say, 100 tiny little hurdles. Each hurdle is easy to clear.
And because each individual EBM in the chain is simple, its energy landscape is also simple. No huge barriers, no getting stuck.
You nailed it. Sampling each step is fast and cheap. But because you chain all these simple steps together, the overall model, the whole sequence, can still represent that really complex data distribution, like separating dogs and airplanes.
That's really clever. You keep the expressive power but ditch the sampling bottleneck. It bypasses the métis entirely.
That's the core algorithmic insight.
Okay, so that's the DTM algorithm. Now, how do you build hardware for that, the DTCA denoising thermodynamic computer architecture?
Right, the DTCA is designed specifically for this chained EBM approach. It tightly integrates the algorithm with probabilistic hardware. What's key is that each simple EBM in that chain can actually be mapped to its own distinct physical circuit on the chip.
Oh, interesting. So different parts of the chip handle different steps in the denoising chain.
Kind of, yeah. And the specific type of EBM they use are Boltzmann machines, sometimes called Ising models. Their update rule is very simple mathematically, which makes it super efficient to implement directly in parallel hardware.
Now, I remember you saying earlier attempts at probabilistic hardware failed because they needed weird materials to get the randomness, the thermal noise. What's different here? What makes the DTCA potentially viable for mass production?
This is probably the biggest hardware innovation they highlight, the thing that unlocks the potential scalability and justifies that huge energy-saving claim. It's an all-transistor probabilistic computer.
All transistor, meaning just standard silicon, like in normal chips.
Exactly. Those older designs relied on things like magnetic tunnel junctions or other exotic components to generate random numbers, stuff that's hard or impossible to integrate into standard CMOS manufacturing, the process used by, Intel TSMC.
So how does the DTCA get its randomness using just standard transistors? Aren't transistors supposed to be deterministic, reliable switches?
Usually, yes, but this is where the clever co-design comes in. They leverage the inherent randomness that already exists at the quantum level in transistors, especially when operating near their threshold. They designed a specific random number generator, an RNG circuit, using standard transistors that harnesses these effects specifically, shot noise dynamics.
Wow, so they turn noise, something engineers usually fight to eliminate, into the core feature.
Precisely. They weaponize the bug. And this all-transistor RNG is reportedly very fast, tiny, about 3 by 3 microns on the chip, and incredibly energy efficient.
How efficient are we talking?
The number cited is around 350 attajoules per random bit generated.
Attajoules, that's almost unthinkably small. For context, how much energy does flipping a normal digital transistor bit cost?
We're usually talking femtojoules for a standard logic gate switch, maybe a few femtojoules. An attajoule is a thousandth of a femtojoule. So that this RNG is operating at an energy scale that's, well, it's pushing the fundamental limits.
Okay, so super efficient RNG using standard parts. Let's connect that back to the system level. How does that, plus the DTM algorithm, achieve the 10,000x overall saving?
It comes down to the total energy cost. The analysis estimates the energy per basic operation in one of their sampling cells, E-cell, is maybe around 2 femtojoules, very low. But the huge gain comes from the number of operations needed. Remember how the DTMs avoid getting stuck? They mix incredibly quickly.
Right, fewer steps needed to get a good sample.
Exactly. The number of iterations needed, CAMX, is much, much lower than for a traditional GPU running, say, a diffusion model or definitely an old MEVM. So you have a very low energy cost per step multiplied by vastly fewer steps. That's where the 4 orders of magnitude primarily comes from. It's dominated by the sampling cost.
Makes sense. The sources also mentioned training. We know the old monolithic EBMs were a nightmare to train because if they weren't mixing properly, they gave garbage gradients. Does DTM fix that too?
It helps significantly, yes. Just the act of breaking the problem into simpler, denoising steps inherently makes training more stable. But they also introduced an extra trick, an adaptive correlation penalty, or ACP.
ACP, what's that do?
It basically monitors how well the model is mixing during training by looking at its autocorrelation. If it starts to mix poorly, if the samples are getting too correlated and stuck, the ACP automatically increases a regularization penalty.
Ah, so it dynamically adjusts the training wheels based on how well the model is behaving.
Kind of, yeah. It nudges the model back towards good mixing, preventing the training process from diverging or collapsing, which was a major headache for the older models.
Okay, so we have the DTM algorithm solving the core sampling problem via meat. We have the DTCA hardware using standard transistors for efficient randomness. It seems like a really complete picture. What's next? How does this scale up?
Well, the models they actually tested in the source papers are still relatively small compared to what the hardware could theoretically hold. They estimate you could fit maybe up to 1 million of these sampling cells on a reasonably sized chip. But their hypothesis for scaling to really large, complex problems isn't just make the probabilistic chip bigger. It's about hybrid systems.
Hybrid. You mean mixing this new DTCA hardware with traditional processors, like GPUs?
Exactly. They call it hybrid thermodynamic deterministic machine learning, HTDML.
HTDML. Catchy.
The core idea is intelligent workload distribution. Use the right tool for the right job to minimize the total system energy. So maybe you use a small, efficient traditional neural network running on a small deterministic chip for tasks like initial data processing or embedding, fast, low-level stuff. But then, for the really complex, computationally heavy lifting, like the core generative process where sampling efficiency is key, you offload that to the probabilistic DTCA hardware.
Interesting. So the DTCA handles the part that current systems struggle with most energy-wise.
That's the idea. And they actually showed a proof of concept for this. They built a hybrid model for the CIFAR-10 image dataset. It used the DTCA for the main probabilistic generation, but had a small, traditional neural network act as a sort of decoder.
And how did it perform?
It apparently achieved similar image quality to a standard generative adversarial network, a GAN, which is a common benchmark. But, and this is the key, the deterministic neural network part in their hybrid model was about 10 times smaller than the one needed in the standard GAN.
10 times smaller on the traditional silicon part. That really demonstrates the DTCA is doing the heavy lifting for the complex generation.
Precisely. It shows the potential of this hybrid approach to drastically reduce the size and therefore energy cost of the deterministic components we currently rely on.
This is genuinely fascinating, seeing how the algorithm design, the DTM fixing the meat, meshes so perfectly with the hardware engineering, the all-transistor DTCA. It really feels like a systematic way to break free from that hardware lottery we talked about earlier.
It does. It feels less like an incremental improvement and more like a potential paradigm shift, a move towards designing algorithms and hardware together, specifically for energy efficiency from the ground up.
So what does this all mean for you, the listener? I think the biggest takeaway is that the immense energy costs of AI we're seeing today might not be an unavoidable law of physics. It might actually be a consequence of the specific design path we happen to go down. And this research suggests there could be fundamentally different, vastly more efficient paths available. We might not have to choose between powerful AI and a sustainable energy future.
But it's not necessarily a solved problem either. The sources do caution that scaling this to handle data far more complex than, say, CIFAR-10 images introduces new challenges. Specifically, how do you efficiently route information between potentially millions of these simple EBM units on a chip? The physical wiring constraints might not match the ideal information flow needed to model really complex correlations in data.
Ah, so even if the individual units are efficient, connecting them effectively for massive problems is the next hurdle.
It seems that way. They suggest we might need fundamentally new graph architectures, new ways of thinking about connectivity within these thermodynamic computers that are co-designed with the data structure itself.
So the final provocative thought they leave us with is, what does that next breakthrough in hardware graph architecture look like? What kind of connectivity will unlock the true potential of large-scale thermodynamic computation? That seems to be the next frontier.